Hello guys, welcome back. For this video, we're going to take a look at the question based on acids and bases. It's a grade 11 question from a previous paper. Now, we're just going to take a dive on the question. 8.1, two reaction of sulfuric acid is shown below in the diagram. So you can see here with reaction 1 here and with reaction 2 here. Now, before we go down to answering some of the problem, we might take a look at the reaction and see what's going on because it's incomplete. You can see here for the reaction 1, sulfuric acid is reacting to a strong base, sodium hydroxide, to produce salt and water. We know that the reaction or the neutralization reaction between an acid and a base always yields salt and water. So the product Y would then represent water there. Now we might as well go ahead and write the reaction. So we have sulfuric acid plus sodium hydroxide. It's going to give us salt X. Now in order for us to find the salt X, we have to break the ions of sulfuric acid and to dissociate the ions of sodium hydroxide. The ions of sulfuric acid are H plus ion on the proton. Remember, the acid is a proton donor and a sulfate. And the ions for the sodium hydroxide is the sodium ion and the hydroxide ion. Now we just need to pair them to get what we're looking for. So from one of the reactants, which is now broken into its constituent or its component ions, we have a positive and a negative ion, and the other one is a negative and a positive ion. All you need to do is just to make sure that the positive ion from one of the substance is bonded to the negative ion on the ions of the other substance. So the H here will be bonded to H or H minus, which gives us water, and the sulfate ion will be bonded to the sodium ion. Now, we bond by swapping the charges. Let's say we have the sodium ion and the sulfate ion. Now this is a -2 ion and this is a positive ion. When we do ionic compounds, all we do is to just swap the superscript into subscripts. In other words, this charge will come down here and this charge will come down here. All right, and then we have to write what those charges are. So if I bring that one down, it's going to be a 2, meaning that I need 2 sodium ion to neutralize 1 sulfate ion. Simple as that. So it's going to be Y, because sulfate here, and you can see sulfate is a 2 negative charge. And if I'm going to neutralize this, remember a compound doesn't carry a charge. So the overall charge of the compound is 0. So what's going to happen is, because the charges will need, if I'm forming a compound, I need to neutralize the charge of those constituent ions. In this case, because these are ionic compounds, so the Na plus, I'm going to need 2 of those to neutralize the SO2 minus, SO4 actually 2 minus charge. However, these ones and this one are basically the same charge with a plus. These same number of charge, not the same charge, is a positive and negative. So this one's going to be where our water molecule formed from. All right. So that's the first reaction. We're going to do the same thing for the second reaction. I'm going to get rid of this. We do, however, have a section on grade 11 where we actually show how you form a unit compound. If you go there, it's under my playlist on grade 11 on formation of a unit compound. Before I actually introduce this topic, that's the one that I start with. So please make sure that you go into that playlist and take a look at how actually ionic compounds are formed. And we form different types of ionic compound, and that will actually bring in more clarity and more understanding as far as this is concerned. Let's take a look at the reaction 2. Reaction 2, there is a sulfuric acid. So we did get from reaction 1, we did get the salt, which is sodium sulfate salt, and then we also get the product Y, which in this case was water. Now the second reaction, we are reacting the sulfuric acid with water. All right, so it's gonna be H2SO4 plus the water. Now the water that's being reacted here with the sulfuric acid, it's gonna act as a base, just like the sodium hydroxide here was a base. This is an acid, it's never gonna act as a base. So the water here is gonna act as a base. Remember, a water is an amphibolite, can act as either a base or an acid. In this case, it acted as a base. Now again, I'm gonna break these ions into H plus. Now notice here, when I reacted this, the ions were H plus and SO4, excuse me, 2 minus ions. But here, it's gonna be H plus and HSO4 minus 1. Why? Because while I reacted sulfuric acid there, which is a strong acid, with a strong base, the H plus ions, they come all together at once. But whenever you react with this, actually it's going to take reaction when you dissolve the sulfuric acid in water. So the first reaction will be this, and the second reaction will be where now you will be left with the sulfate ion, hydrogen sulfate ion, excuse me, and then it's then added to water. Why? Because the first hydrogen does come out, but the second hydrogen is hard to come out when dissolved in water. Well, it may do that for that one, it's not going to do that for this one. Well, because water is not as strong to neutralize as the sodium hydroxide, because sodium hydroxide is a strong base. And by the way, this is called the neutralization reaction. However, this is ionization reaction. So when breaking the ions of this sulfuric acid, the second ion or hydrogen ion does not come out in the first reaction. However, it's going to come out in the second reaction. So it will look more like this. This hydrogen will be donated to the, remember, sulfuric acid is an acid, is a proton donor. We're going to have hydronium ion plus what we're left with, hydrogen sulfate. And then that hydrogen sulfate will further be reacted to water. And then again, that's when we're going to break to SO4 2 minus with H plus here. Again, this H plus will be donated to the H2O. In this case, we have H3O plus sulfate ion. However, this is not the reaction they wanted. They wanted the first one. So I wanted to illustrate to you how actually do we come into conclusion as far as the first one is concerned. However, this one you can scratch out. They didn't want that part. Alright, so we have the two reactions that they requested from us, and there they are. I'm just going to clear the space. Alright, now we have the reaction 1 and reaction 2. So in reaction 2, we have the H3O plus, that will go in the amphibolite. Now, you may change the position for this one to just make sure that they're in that order. I'm just going to go ahead and do that. So it's hydrogen sulfate plus the hydronium ion. It's a positive there. Alright. Now that's the 1 and the 2 reaction. So this reaction 1, this is reaction 2. Don't confuse with the ones that I did. Those are two types of reaction, or two stages of reaction with water. Sulfuric acid actually is dissolved in water. Now let's go ahead and take a look at the questions. The first question, 8.1, I'm just going to take the first question, second question, and then the third one. The first question, 8.1, they want you to define a Lowry-Bronsted base. Remember, in our definitions or our acid-base models, we have two types. The first one is the Arrhenius acid-base model, and the second one will be Bronsted-Lowry or Lowry-Bronsted acid-base models. Now, these models describe or define actually a base and an acid in different forms. But in this case, they want us to define this one. Now, I don't want to take more time into that. We're just going to go ahead and 8.1.1 will be a proton donor. That's what a Bronsted base. Actually, it's a proton acceptor. The donor is the acid. So this is the proton acceptor. Excuse me. Now, the second equation, 8.1.2, write down the balance equation for reaction 1. Fortunate enough, we've already covered that part. The reaction 1 is sulfuric acid with sodium hydroxide, which gave us sodium sulfate and water. Now they want a balanced chemical reaction. Now when balancing acid-base is neutralization reaction, I always advise my learner to start with the salt which was being produced. And if we start with the salt that was being produced, you just balance the cation there, which is this one, and then you balance if basically it's reacted with a polyatomic ion, and you then balance the other substance, and except for oxygen. A lot of polyatomic ions have oxygen in them, but just balance the other element except for oxygen, and then move to the hydrogen, and the oxygen will just automatically be balanced. So I'm just going to go ahead and do that. You can look on the right where we have sodium sulfate. We have 2 of sodium sulfate. So I'm going to make sure of sodium actually. I'm going to make sure I have 2 sodium here as well. All right. Now there's balance. You look at sulfur, obviously it's automatically balanced. We have 1 sulfur here, which gives us 1 sulfur there. I'm not gonna count the oxygen. I'm gonna move right away to the hydrogen before I do that. On the left hand side, I have 2 hydrogen and another 2, which is gonna give me a total of 4. However, on the right, you can see on the water molecule, it's only 2. So I'm gonna multiply that by 2 to get a 4. And by so doing, you're done. The reaction is balanced. If you may ask me, what about the oxygen? Now, like I said, it will automatically balance. As long as you've done everything right, the oxygen will automatically balance. All right, you may check to confirm, but that's the case. So let's go to the equation 8.1.3. They want you to write the name of the salt represented by X, and that's the name of the salt. We do have the formula for the salt compound, which is sodium sulfate. So we're just gonna write it, sodium sulfate. Writing the name of these salts is very simple. You start with because mostly they start with the metal in group 1 or group number 2, or some transition metal. Just mention the name of the metal or write the name of the metal in full, and then finish with whatever polyatomic ion. Sometimes it can be like monoatomic ion, but you write that name of the ion in full. If it's 1, the suffix will be IDE. If it's a sulfate, it's going to be sulfate. Nitrate is going to be nitrate. With different types of these names, by the way. And like I said, that's where we learn in full how to make this compound. But this is a totally different subject altogether. All right. Now moving on, we'll be going to 8.1.4, and then we're going to take the other one. All right, let's go ahead and look at 8.1.4. Now 8.1.4, they want us to write down the formula for the ampholyte A. Now, it's good that we've done those equations first, so it's pretty much simple for us to just do that. So the infinite A is this, the hydrogen sulfate. They want the formula, so we did give them the formula for the hydrogen sulfate ion. That's 2 marks, pretty much easy. And then 8.1.5, write down the formula of the two conjugate acid base pair in reaction number 2. I'm just going to go ahead and copy and paste reaction number 2, and so that you guys can understand what we should illustrate as far as that question is concerned. All right, that's reaction number 2. Might as well go rid of the 2 there. All right, in these, they want us to find the conjugated acid base pair. Actually, they're looking for 2 conjugated acid base pair as being highlighted for us there in capital letters. Now, how can we identify a conjugated acid base pair? How I do it with my student is we just take a look at the same things, like we're looking for same identical things but with a difference of H. One of them will have 1 H extra, and the other will have less 1 H, but everything is pretty much the same. You can see that this and this don't look the same, all right? But this and this does look the same. So those will be conjugate, all right? That's how you save your time with these guys. And then these and these quite look the same. So you just look for what has the difference of H. It's either one has an extra H and the one has 1 H less. But they are basically the same elements, same everything actually, except for the difference of H. One has H extra. So here I have 2H and here I have 3. But other than that, the elements are the same. So that's how I actually identify the conjugate acid base. It's quick to do it that way because I figure that talking about the rest of the stuff is quite confusing. So we have sulfuric acid and hydrogen sulfate. And the second one would be the water molecule and hydronium ion. Now they're going to give you 4 marks for that. Moving on, we're going to go to 8.2. So 8.2 is actually 8.2.1 and 8.2.2 question. All right, and that will sum up the entire question. All right, now let's read the question. 8.2 says a solution of sodium hydroxide, whose formula is given to us here, is prepared by dissolving 6 grams, that's going to be useful, of solid sodium hydroxide in 500 cubic centimeter of water, or centimeter cube of water. Now the solution completely reacts completely with 10 grams of impure ammonium chloride according to the following reaction. So this is the reaction where the solution, which is found here, right? So when something is dissolved in water, like for example your sodium hydroxide is being dissolved in water. Now to dissolve sodium hydroxide in water is basically to react sodium hydroxide in water. The reaction will look more like that, or maybe like this. So that's a dissociation. I want to just illustrate that. So when sodium hydroxide is dissolved in water, that will give us a dissociation of sodium hydroxide into Na plus OH minus, right? Now these make sodium hydroxide a solute, and the water here is a solvent. We know that water is a solvent actually. So the water is the one that occur in a larger proportion. In this case, this will be the volume of the water, 500 cubic decimeter. So that's the volume of water. So I'm going to write here 500 decimeter cube will be my volume for water. Now we're going to talk a little bit about volume in a second, but just wait for me to illustrate something. So if of the volume of water and this is dissolved as a solute, is dissolved in this. Now what we know, you can think of it like this: if you take salt and dissolve it in water and make sure that it is dissolved, like fully dissolved obviously, or maybe sugar and dissolved in water, you taste in every molecule, if you may think of it like that, but in every part of water you're going to taste that salt which is there. So there's no water that doesn't have that salt. For example, if you make tea and then pour sugar, the same taste is consistent, taste already, not taste. The same taste is consistent throughout the liquid, or the liquid water, or the liquid whatever the mixture will be. So I think in grade 10 that's where we learn a little bit about these in terms of types of mixture. That will be more a homologous mixture. It has a consistency throughout. Now that means for us that the volume of water will be the same volume for the sodium hydroxide, in a sense, because the sodium hydroxide is dissolved in that volume of water. I think I wanted to just illustrate that idea. All right, so the solution of sodium hydroxide, which will later be reacted with sodium ammonium chloride, is what I'm interested in right now. So the solution of sodium hydroxide is prepared by dissolving how many grams? 6 grams of sodium hydroxide. So we have 6 grams, that's the mass of sodium hydroxide, will be dissolved in that. So this is more of a solid mass. If you may think of it, they did also mention it's a solid sodium hydroxide, which will be dissolved in that. All right, so if it's dissolved in that, the same volume of water will be the same volume for the dissolved solid sodium hydroxide. All right, it's no longer solid then after being dissolved. So the equation, however, in 8.2.1, I think is somewhere along the lines where we'll need to find the concentration of the sodium. Calculate the concentration of the sodium hydroxide solution. So if they're looking for the concentration of sodium hydroxide solution, we need the number of mole. The concentration, we need the number of mole, and we're going to divide that by the volume, right? Remember, concentration is the amount of a solute in the volume of the solvent. So we are looking for the amount of the sodium hydroxide in the volume of what do we call them, of the water, which is the solvent. All right, in order to do that, we're going to need the number of moles, and then we're going to divide it by volume. The volume, like I said, is the same volume. However, our volume should be in cubic decimeter. So let's say the volume of sodium hydroxide is 500 cubic centimeter. Now, which is the same as the water. Now your volume should be divided by 1,000 to get a cubic decimeter. So if we take 500 and divide by 1,000, we get a 0.5 cubic decimeter. Just move your decimal 3 units to the left, and then you get a 0.5 cubic decimeter. So that's the volume that we're going to use for sodium hydroxide here. But the number of moles, however, are not given us here. Now, maybe I think that's where the 4 marks come from. We're given, however, the mass. Now, in order to do that, we'll first need the number of moles by using the equation mass divided by the molar mass. If you take the mass of a substance divided by its molar mass, you're going to get the number of mole. What is the mass of the substance? So the mass of the substance is given to us is 6 grams. But what about the molar mass of the sodium hydroxide? For the molar mass of sodium hydroxide, you need to go into the periodic table to check for the relative atomic mass of sodium, oxygen, and hydrogen, which makes the sodium hydroxide compound. So we're just going to do that. I'm going to just scroll right away to the periodic table. Now the purity table is given for you guys, by the way, on the back or at the back of the question paper. So it's not something to worry about. What we're looking for here is the relative atomic mass of every element that makes up sodium hydroxide. The sodium is 23, so I'm gonna put 23 there. Plus oxygen is that number, is this one, 16. So I'm gonna put the 16 there. Plus hydrogen is 1, so I'm gonna put the 1. It's 1, so I'm gonna put the 1. So add those numbers together, they're gonna give you the mass of the compound sodium hydroxide. So let's say 23 plus 16 plus a 1 is gonna be 40. So the sodium hydroxide gives us 40 grams per mole, meaning that 1 mole of sodium hydroxide contains about 40 grams. So that's exactly what we're gonna put here. The mass again is 6 grams divided by the molar mass is 40 grams per mole. And then the grams and grams here will cancel, as you can see. The unit grams cancel the unit grams. I have 60 divided by 40. If I take, 6, not 60, divided by 40, it's going to be 0.15. So the number of mole of that are going to be 0.15 mole of sodium hydroxide. So those are the number of mole. Now the number of moles are going to now then be placed into that equation. So the concentration is going to be number of mole divided by volume. The number of mole I just calculated here is 0.15 mole. The volume is the same as the volume here for the water is 0.5 cubic decimeter. Now you just simply take a calculator and just find that out. So we have 0.15 divided by 0.5, which is going to give us 0.3. So the concentration is 0.3 mole per cubic decimeter. So that's your concentration of sodium hydroxide. So we did find the concentration of sodium hydroxide. However, if we do take a look at the same question paper, I'm going to scroll where we have a set of equation. Now you can see 2 equations here. The equation that we use is that one. Now you see another equation that they said that you can use these or these. All right. So one of the 2 equations will work for what you're looking for. Now using this equation will have you use this equation and that equation as well. And you've seen that's what I actually did. In order to use that equation, I've used that one first and then came to use that one. But however, when you use this one, you don't have to combine the 2 equations. And this equation is a combination of that equation and that equation. So sometimes you can just plug that equation alone and then you'll find what you're looking for. So the concentration will be the mass divided by the molar mass times the volume. If I use that equation, I will have to put everything together. Like I said, it's a combination of both. Because molar mass divided by the volume, actually divided by the mass divided by the molar mass is the number of mole. And then if I multiply by 1 over volume, that will give me the concentration. So you can use that equation. That's going to be 6 grams divided by the molar mass is 40 grams per mole, like we said. And then we're going to multiply by the volume, that's 0.5 cubic decimeter. All right. And then when you punch the calculator, you should get 0.3 mole per cubic decimeter. Grams and grams again cancel. And then I think we are done. All right. Now if you use those 2 equations or one of those equations, whichever one you're comfortable with, you'll find they'll give you the total number of marks, even if you did use this one. So there's no difference. Now let's go on and take a look at this next question. All right. So these 0.5 mole, the 0.5 mole, where are they? These ones. 0.15 mole of sodium hydroxide. We're going to come back to them in a second, I'm sure, in the next question. All right. Let's take a look at the next question. The next question, they want us to calculate the percentage impurity of sodium chloride. Let's just read a little bit here. Here we are told that the solution completely reacts with 10 grams of impure ammonium chloride. So this is the mass of the impure sample. The equation that we're looking for is for percentage purity. We don't have an equation for percent purity. So the percent impurity is the mass of a compound. In this case, our compound is sodium ammonium chloride divided by the mass of a sample. So we're going to be given a sample of an impure substance, and that's going to be the number that goes in there. That number, I think, is given to us. We told the 10 grams. So the 10 grams is the number that comes here. Here, 10 grams goes in there. After that, we're going to multiply that by 100. Why am I putting that number there? So that you can know actually what we're looking for. It's easy to find what you look for if you know, because you don't get mixed up with the question and try to understand what is it that you're trying to find. It's easy when you know what you're looking for. The question then becomes, in everything, in this equation we have everything with this and that. We only actually need 3 things. The question is, what is the mass of a compound? The mass of a compound here is the mass of your ammonium chloride. So the mass of the ammonium chloride is the mass of the ammonium chloride that reacted, in terms of grams, that reacted with the sodium hydroxide. So in order to find the mass, we need to find the number of moles of the number of moles of ammonium chloride that reacted with, I'm getting ahead of myself, with sodium hydroxide. So if we have the mole of sodium hydroxide, we're going to get the mole of what? Ammonium chloride. What are the mole of sodium hydroxide that reacted with the mole of ammonium chloride? Go up and read an equation. A solution of sodium hydroxide is prepared by dissolving 6 grams of solid sodium hydroxide in 500 cubic decimeter of water, centimeter actually of water. Now this solution reacts completely with 10 grams. That solution, meaning that the same number of mole are the one that react with the sodium hydroxide. Because from this solution is where we found the 0.5, the solution which has a concentration of 0.3 as the number of mole of 0.15 mole. So with that being said, we're going to use the same number of mole to find the moles of this one. And after finding the moles of that one, we can find the mass of that one. And then we can use the mass in the equation of percent purity. And whatever percentage we get, we subtract that from 100. We're going to get the percentage in purity, because that's what they're looking for. They're not looking for percentage purity. Let's go ahead and do that. I know I've quite explained it a little bit quicker, but that's what happens. The key is I need to find it. How can I find it? I need to find the number of moles of that. How can I find the number of moles? Stoichiometry, I'm going to compare. Sodium hydroxide is said to react with ammonium chloride to give me sodium chloride plus, to give me sodium chloride plus, I think, water and ammonia. I'm just gonna check and just to confirm. I think that's the case. So it's water and ammonia, yes. All right. So I need to find the mole ratio for this is 1:1, because what I'm given actually is the balanced chemical equation. All right. They say it according to the equation below, but they didn't say according to the balanced equation. So we cannot assume. Let's just first try to see if the equation is balanced, because we might get wrong feedback. All right, I have sodium 1 on the left, 1 sodium on the right. Oxygen is 1 only on the sodium hydroxide. I only have 1 on the water molecule. and then hydrogen is 1 and 4 here. It's going to give me a total of 5. I have 3 here and 2 here is going to give me a total of 5. 1 chlorine, 1 chlorine. All right. So it's a balanced chemical equation. So the mole ratio between this is 1 and 1. And why? Because that's exactly what I'm going to need. The number of mole of sodium hydroxide to the number of mole of ammonium chloride is the mole ratio is 1:1. Why? They're reacting in equal ratio of moles. Meaning if I have 1 mole of sodium hydroxide, I'm going to get the same 1 mole for ammonium chloride reacting. But how many moles of sodium hydroxide do I have? I have 0.15 mole. These are going to be the same number of mole of ammonium chloride because that's what I have for sodium hydroxide. So they react in equal mole ratio or in equal molar. I can't say molarity, that's concentration. In equal mole ratio. So now that I have a number of moles for this, I can then use the number of moles is equals to the mass divided by the molar mass of the ammonium chloride to get the mass of ammonium chloride. After that, I will be done. All right. So I do know the number of moles is 0.15 mole equals the mass divided by what's the molar mass. Again, the periodic table. The molar mass of NH4Cl will be found in the periodic table. We just look for the relative atomic mass of each and every element in the ammonium chloride compound. Let's go ahead and do that. The nitrogen is 14 plus hydrogen is 1, and I have 4 of them. There's going to be 4 multiplied by 1 plus chlorine. Let's go ahead and take a look at chlorine. There we go. It's 35.5. Now I just need to add the numbers together. So I have 14 plus 4 times 1, which is a 4, plus 35.5. That's going to be 53.5. That's going to be 53.5 grams per mole. So that's the number that I'm going to put here, 53.5 grams per mole. You should remember that the units are not really required. You may just put the numbers alone. They're not going to penalize you. But I would advise you to just put, whenever you calculate the molar mass or the molecular mass, just make sure that you put them in your paper because they will mark those. From this point, we can cross multiply 0.15 mole and then multiply that by 53.5 grams per mole. You can use this. I know a lot of you are used to mole with a -1, and that's going to give me the mass. The mole and the per mole, they're going to cancel. I'm left with grams. So 0.15 multiplied by 53.5. It's going to give me 8.025. So that's the mass. That's the mass of ammonium chloride. This mass of ammonium chloride is the mass of a compound, like I said in this equation. So we're going to put there. Again, let's put the equation again. The percentage purity is the mass of the compound, which we just calculated here. It's going to be 8.025 grams. I'm going to divide that by the mass of a sample. The sample of impure substance or impure ammonium chloride is 10 grams. And then multiply that by 100. Grams cancel. Just going to be left with the numbers and multiply that. Going to give us a percentage. So it's going to be 8.025 divided by 10. That's going to be 0.8025. So it's 0.8025. and then we'll multiply that by 100. We're gonna get 80.25%. So it's gonna give us 80.25%. That's gonna be your percent purity. However, the question was looking for percent impurity, not percent purity. Now we need to find how much is left from the 100%. That would be a percent impurity. It's going to be 100, minus 80.25. If you subtract that from 100, this is percent pure, right? And it means that whatever is left behind, which is 19.75, will be percent impure of ammonium chloride. Take a look at that against 9.75. Right, there we go. So that's actually the answer that they wanted. Took a long time to get to that, but as long as we understood what the idea, or actually what is it that we're trying to look for, doesn't matter how long it takes, you won't get lost. With a little bit of practice, you'll be able to do what you're supposed to do. I think that was the last part of the question. And with that being said, I wish you good luck and enjoy studying.